So in terms of materials, I do have a PowerPoint up on Canvas. I additionally have one part that I did add. Uh, I think it's labeled as like an I-beam, and we'll take a look at that kind of later, probably at like the very end of class after we discuss some of like the final topics. But for the most part, I think the two topics that I have listed in the PowerPoint are things that we will be making. And before I do that, I'm actually going to see if I can add the, possibly add the images of those drawings to the chat, just so that it'll be a little bit easier to see for everybody. Let me try doing it this way. There's the first part that we will discuss, and the second part that we'll discuss. Okay. I'm just going to get started, and people can sort of filter in as we're going. Um, so I know I went through at least a bit of information the other day in terms of just some basic things going forward, but tonight is going to be our last formal lecture. Next Thursday, we will have our second exam, and then sometime between this Thursday and next Thursday, I will have a rubric provided that will discuss the final project. So, in terms of the final project, I will likely be grouping you guys up however I see fit, hopefully in a reasonable manner. And then you guys will kind of be functioning as a team to try to create whatever sort of assembly type uh, thing that I give you. So once the rubric is put out, it'll make a good bit of sense as to what you guys are working on, and I'll make sure to let each of the individual groups, either by way of like a DM or an email, what you guys are supposed to be modeling and creating and making like all your diagrams and parts and such for. Um, Other than that, and I do want to have a little bit of a discussion about this later once we are done with the lecture tonight, but I am curious about how some people feel about what we could do for the second exam, or what I could give you guys for a second exam. As I mentioned, as it currently stands, I have an idea of it being two questions, pretty much what I just discussed, one in which I would be providing parts, and I would ask you guys to make an assembly and a drawing for that respective assembly. Um, and then the other option is and the other question would be a simpler assembly where you guys would not only be creating the assembly and the drawing, but you would also have to be doing or creating the parts as well. The third alternative that I'm kind of thinking of as well could possibly be only a single question, but it's a bit of a trickier assembly to make or trickier parts to make, which uh, to create whatever assembly that I would be asking of you guys. So think about it for right now. We can talk a little bit about it later on once we're done with the official lecture, just so that you guys can kind of think about it, and then we'll talk about it after. And I'll make sure that a rubric for that final project gets put out, as I said, before the next lecture. So in terms of today's lecture, we are going to be talking about kind of a handful of things. I did compile a bunch of different stuff, but it's about 20 slides, so it's not a lot. Each of the things are, by this point, I would say, or at least the first couple things are reasonably intuitive, so hopefully it isn't going to be too crazy for anybody, given that we're more than halfway through the semester, so everyone should feel reasonably comfortable to kind of tackle a given engineering drawing and make those respective parts. So the first thing that I want to discuss is using 3D sketches. So I know that some of you guys have sort of used this before, or possibly played around with alternative ways of doing this. However, we can create 3D sketches, and 3D sketches are actually really helpful to create geometry or just sketches to then further create geometry without actually necessitating something like a datum plane. So we can use these in instances where we might have some good reference geometry that's already built within our part. Um, and then going forward, it kind of makes things a whole lot easier to either create extrudes or extrude cuts or whatever we might have to do. So it's a good way to really remove having to create datum planes from the equation. That's not to say that datum planes aren't important, because there are certain aspects that using a 3D sketch will not be able to accomplish. So we want to be able to keep that in mind when we're creating our 3D sketches. So I would try to ensure that whenever we're creating any sort of 3D sketches, we're more focused on really basic extrusions or extrude cuts, possibly some other features that I can't really think of right off the top of my head, but I know some that don't actually work. So if we're taking a look at SolidWorks, or actually first and foremost, I know I posted it in the Discord, but there is a first part that we can see if we can take a stab at creating. So I hate the picture because it's a little bit small, but that should be fine. Most of the measurements are at least fairly reasonable in terms of being able to read. So for the most part, if we're looking at this part, let's try to, just generally speaking, break down what we might want to do first in terms of creating this. I'm seeing that we have two rectangular prisms that could just be stacked on top of one another. So that might be the first approach that we want to take. It's also telling us that we have a material of ASI 304, units are in inches, and we're given a mass. So let's just start building this right now. So I'm going to take the top plane and I'll just make that base. And by the looks of it, it looks kind of like it was, yeah, so it has a width, it's looking like, of about 5 inches and a length of 2.5 inches. And I'll make sure that I'm in IPS, and that's fine because we can now extrude this here. I believe it's saying that we have a 2-inch height there. I think I have it labeled. Yep, we have a 2-inch extrusion from this, so it'll be 2 inches high. And then we want to make sure that we can create that other kind of smaller looking box on top. So we'll draw on this plane as well. And I'll make this a corner rectangle just because it'll be that much easier to actually create that box. It's 0.6 inches, and I think this was an inch extrusion. Okay, so getting to this point really shouldn't be that crazy. We should have a fairly good idea of how to create this shape right here that we see, and that's pretty much where we are in the PowerPoint as well. We're able to get to this point where we have this two-tiered boxes, or these two rectangular prisms that are stacked on top of each other. However, now we have two other features that have been added here. Not only do we have something that looks like, almost kind of like a rib, But we also have this thing that looks like a very large chamfer that's also a part of our drawing. So we could rib this, but what I actually noticed is that ribs don't really play that nicely when you're trying to go right up to the edge here. So we do have a couple of options. One of our options could just be, all right, well, we might want to sketch on this plane, make some sort of right triangle, and then extrude it outward. That would probably be one of the easiest methods to go about. So we can do it in that manner, and I think that's a good way to at least go about this first and foremost. Nice thing about this is that all three of the reference points for that triangular shape are really just vertices. So we don't even have to smart dimension anything, it already does it automatically. And then we can just extrude this in the appropriate direction. So flip the direction. I think it said it was zero point 0.7 in that case, or not 0.07, but zero point 0.7. There we go. However, we also could have done something else here. We possibly could have created, much like how we would have created, say, like a datum plane to do a rib here, we could have created a datum, or not even a datum plane, but we could have actually done a 3D sketch. And I'll show that after I show how we can create a nice cut for this chamfer here. So I mean, like I've already said, you could consider this to be like a very asymmetric chamfer as what's seen on the PowerPoint, but it might even be nice to try out using this 3D sketch. So if we go into Insert, near the bottom of the list, I know you guys can't see it that well since it's cutting out that as a window, um, but it's kind of near the bottom. I would say it's about like 2/3 of the way down the list. You should see something that says 3D Sketch. Now 3D Sketch just opens up the Sketch tab now. We can see it indicated by the fact that it has the same sketch symbol, only it has a 3D in it. And this will allow us to basically place points or lines or geometry in any direction. So I'm not really restricted to a single plane anymore, which can be very beneficial depending on how weird our geometry might be or what kind of weird cuts we might have to make. So if we're looking back at the drawing real quick, it looks like the three, I mean, you could consider that face. I mean, it is a triangular face there, and it's telling us that the two corners, or rather two corners of that triangle line up with vertices that are already there, and that third vertice is 2.15 inches away from this edge right here. So what we can do is we can just start off with a line, and I can select anywhere. It's uh, I believe it's around this point that's already given right here, but just so we'll be able to smart dimension it, I'll just place it in a random location. And we'll notice that it kind of is moving in just one plane here. However, when I shift my view, if you look around while you're trying to do the 3D sketch, you can see that it's moving in different directions. And even when I move it out over this way, it's moving it basically in plane. So it's pretty nice because it allows us to really go anywhere that we want. It's a fairly effective way of doing things. So somehow I selected a circle, so I'll just reselect the line it up right over here, and line it up there. And then the only other thing that I want to do is just make sure that this is smart dimensioned appropriately. So it's telling us that this distance right here should be 2.15. We'll push that out. And nicely enough, it already has smart dimensioned everything because most of these points or vertices of this triangular face are reference points to something else that already exists. So that is pretty beneficial when we're working on this. So now we want to basically cut this. So we'll do an extrude cut. But we'll notice that even though we have a sketch, normally when we're trying to do a sketch, or rather an extrude or extrude cut, it shows a ghost image of it. Here we don't even have that sort of, that yellow like image of what is actually being extruded. And the reason for this is because it doesn't actually know, SolidWorks doesn't actually know where to start extrude cutting from. So keep in mind, it has many directions that it could start this extrusion from, almost kind of like if you're thinking about loft. Uh, it could start extruding normal to this shape, however, it could start just curving to the left or to the right or in some other given direction. So we need to actually give it a direction indicated by this blue box to create this extrusion. So thankfully, most of the directions that we have um, work pretty much as you would expect. I want to extrude it outward or extrude cut it outward to the right. So I'm going to select this edge right here and then just ensure that it's going out an appropriate distance. So one manner is I could literally just bump up the distance, but I could also change it to a through all. So that means that the lowest point, lowest being used loosely as a term, is going to be on that face of the geometry. If I wanted to, I very easily could have selected that face, and then I would just have to ensure that the dimension is correct. Since it's just a face that we're concerned about, this edge versus that edge is not going to make a difference, so long as you're able to grab a given edge. If I wanted to, I could have grabbed either of these two as well, because they are parallel to the direction that I want it to go. So that's simply a method of going about creating that extrusion that we have here. If I wanted to, I could do the exact same thing with this sort of ramp as well. Just to illustrate that, I'm just going to suppress it, and then I'm going to do another 3D sketch. So I will go back to Insert, and I'll select 3D Sketch. And I'll just select the given regions that I know that the extrusion is going to be a part of. So I'll just click an arbitrary point out here and then make sure that it's part of this vertex up top here. Same deal with that one. I really don't know why it's trying to do some sort of rounded curve here. It can be a little bit funky, I've noticed. But as long as you're kind of straight with your lines and ensuring that they're going in the correct place, then that's fine. So this is about what it looks like. And then for the most part, we just need to ensure that our dimensions are, or relations are correct. So I'll just make these two lines here parallel so they work out just fine. And I'll ensure that this has the appropriate distance of what it's supposed to be. So it's not 0.58, it should be 0.7. And then very similar to what we would see before, we'll do an extrusion for this, but all the same, it doesn't really know what sort of extrusion to do because it is on a very weird angle right now. So I could assign a direction like that, and it's clearly not going in the correct direction, so I'll flip it. But now it's going totally not in the manner that I want it to. So I probably could just do an up to surface, perhaps. Neither of these options really work terribly well. I mean, you probably could do something like an up to body, but that's still not working fairly well. So I would probably choose a different edge. I might choose, say, this edge here, and then flip the direction. And then just make it blind, but ensure that it's going in the correct direction. When I select that, it creates that exact same geometry. So just as what I've said before, just two different ways that we can approach this problem here. Uh, 3D sketches are a very good way of being able to kind of create some more unique or complex geometry without having to use all of the different features that we have available. So there wasn't really any reason to do a rib here because I could have just done either a basic extrusion since it was flush with this surface here, or I could have just done an extrusion from a 3D sketch plane in order to create that. And then we can always create the hole that's up top here, but I feel like most of you guys already have a pretty good idea of the hole wizard by this point. We can go through it a little bit later if anybody wants extra practice, but I don't think it's really that necessary right now. So in terms of what we also have left, or what we can also talk about, is we can now start going through both variables and equations. So variables and equations are actually pretty helpful depending on what sort of project you might be working on. Um, Utilizing some like either variables or just making certain dimensions driven upon other dimensions can be a very great way of parameterizing your parts or making them parametric, making it so that when you change one number, other numbers are going to change accordingly, according to very specific relations. So what we're going to do here is we're now going to start talking a little bit about variables and sort of variables and equations. So generally speaking, whenever we're dealing with variables in SolidWorks, we want to make sure that these variables are going to be independent variables. So we don't want to throw in a variable, not to say that you can't, but we don't generally want to throw in a variable that is dependent upon another global variable. We want to make sure that if we have one single variable, then there are other equations, dependent equations, that are drawing upon that independent variable. I know, throwback to some algebra here. So there's a couple different ways. You might be seeing that on my end already. I have an equations folder that's already here. It's empty, doesn't have anything in it. And even if I open up a new part, I still have that there. So I didn't have that there before, but I feel like going forward, and I think some of you already have it on your parts as well, but I think that it's a good thing to have there. So if you want that to show up in your part, you want to go to your options menu. I think by this point, most people have a pretty good idea of where that little options gear is. For me personally, it's just at kind of like the almost the center top of my screen. I think for some of you who your SolidWorks screen is maybe a little bit more compressed, it might be further on the left-hand side. It should be basically right next to the rebuild button. So if you go into the options menu and if you search equations, the first option that should come up should say System Options, Feature Manager, Equations. If you select that, it should highlight a folder that looks very similar to our equations folder, and it will likely say automatic. I have mine set to show right now just because it's a lot easier to access the equations if it's literally right a part of your features tree. So in the event that you don't already have that there, we can just insert equations as well, or we can create equations. We would need to go into our Tools tab, and kind of in the same region as where the 3D sketch was, you'll see something that's labeled equations. It should have a capital sigma that's just to the left of it. And when you select this, it should allow you to access any of your equations. So we're not really going to go too much into that. We're going to create another geometry first, but we might assign some global variables here in a second. In fact, we might actually do that right now that I'm thinking about it. Yeah, so on the following page, or on the following slide, we see another drawing, and this one is the one that I just provided a little bit ago in the Discord. So I would say this one is at least the geometry itself is for the most part far simpler than the one that we previously had. However, the distinguishing factor here is that we have very few numbers. We, generally speaking, right here just have a collection of variable terms. So either variables or variables with some sort of a coefficient in front of them. So if we're trying to create this, well, then we certainly could just evaluate everything, but depending on the complexity of the part that we might be working with, in addition to whether or not we want that part to be parametric, so we want to be able to make small adjustments to those parts, it might make things harder to actually take that approach. It might be harder to look at the number, look at the constant that's next to it, figure out what that value is, and then select that appropriate value. In addition, if you do have variables that are already integrated into your like equations tab, that just means that any equations that are derived from those variables will change and rebuild the assembly, or not assembly, but the component appropriately. So if you have one or two variables and you adjust them as necessary, and you know that plenty more uh, measurements within your part are dependent upon those variables, those will change as well. So depending on what you're trying to do, that could be a beneficial thing. So back to this specific drawing here, we're told that we have three global variables. And as you know, just like what I said before, all of these variables are constants. We want to make sure that any time that we're really working with this stuff, or working with global variables, we're not assigning things that are sort of uh, nested, if you will, where we have one variable that is in relation to another variable. It just increases the complexity unnecessarily when we can use equations instead. So I know on my part you're not going to be able to see the window, but I'll try to be as specific about those things as possible when going through it. So the first things first, let's just ensure that our variables, our global variables, are integrated in with SolidWorks right now. So if we right click on the equations folder, the very first option should be labeled Manage Equations. And this should open up a little window where we have a couple of different columns here, the first of which is just the names for the three main things that we're going to be working with. I would probably speculate two, because we're mostly going to be discussing global variables and equations. I'm really not too sure about the functionality of features. And I know that your equations can get uh, very unique, for lack of a better term. So you can do some really cool stuff with some of these equations if you know a lot about how to input them and the syntax and all that. But let's be very simple about it. So under global variables, there's a white box that says add global variables. So here, all I want to do is I just want to add each and every one of those variables that we've assigned. Or the variables that were in that SolidWorks drawing. So our first variable a, I'll type a into the global variables box, and then I'll just hit enter. It'll direct me to that second column which says values and equations. And now we can actually do a whole bunch of stuff. One thing is that we could actually create functions based upon a specific measurement or based upon uh, log functions, square roots, trig functions, all these sorts of things. So depending on how complex you might want to make these equations, you can really parameterize how your parts look. But these global variables are going to be very simple. So in that equations or value slash equations tab, we're just going to make it, I believe it's 20 millimeters. So if you add the mm or millimeters to the end of your 20, it will specify that that is a specific measurement rather than just a constant. I wouldn't say it's entirely necessary, but it is good to add just to ensure that things are consistent. And if I am looking correctly, yes, we are dealing in millimeters. So we'll just input all of those constants that are there. So we'll say, all right, well, for our next global variable, it's going to be b. The equal sign should auto-populate, but if not, you can just put in equals and then 10 millimeters in this case. And then yeah, sometimes it might double up the equal sign. So just make sure that there's only one equal sign there. And then for the last one, for our global variable c, we'll make sure that it is 16 millimeters. So now we have three different global variables here. We have a, which is 20, b, which is 10, c, which is 16. And frankly, if you wanted to, or if certain circumstances, all of these could be rearranged in such a way, or put in such a way where where two of those variables could be dependent upon the other. I mean, obviously, if you take half of A, you'll get B, and if you take what, like 4/5 of A, you'll get C. So there are ways that you can approach these, but or create other equations that are dependent upon those variables, but I wouldn't say it's entirely necessary. Um, but mostly what we are going to do now is let's just start creating our part, but let's make sure that we're integrating in the variables that have been assigned. So I'll create a sketch and I'll create a center rectangle on the top plane. So I have this here, and our diagram tells us that the dimensions of the base are going to be 5a and 2a. So if we're looking at this, then we can easily say, all right, well, one measurement, it's basically going to be, what, a 40 by 100 rectangle here. But we don't even need to just know what that measurement is if I want to, and it auto-populates with the 123 that's there already. But what I can do is I can hit equals, and then when you hit equals on a smart dimension, you'll actually get some extra options. The first of which being global variables, and then functions and file properties. If we go into that global variables tab and then select the appropriate variable, so in this case A, it'll populate it with that appropriate measurement. And then we can just do a multiplication sign times 5 and hit enter. So now we'll actually see that not only is this the correct measurement, but if you're looking at Smart Dimension tab, you should see that same capital sigma. You can actually click on that, and when you click back and forth, it'll show you both the value to be displayed, or it'll go back to the equation that's there. And now we can smart dimension the other measurement appropriately as well. And you probably are noticing something that has showed up now. Um, you may have noticed that we have a red sigma that is here on our measurement as well. So that's actually an indicator that we have an equation going on here. So we have these two measurements now which are driven by some sort of global variable. So this is actually pretty good. It's a good factor because now we can determine in our oh crap, you guys can't hear me. Oh, hold on, let me see. How about now? Can you guys hear me? Hopefully.
Yes.
Okay, perfect. I don't know what that's all about. I guess Discord is throwing a fit. Uh, I was wondering why all you guys were jumping in and out of the call. All right, so you might have to rejoin or relook at the stream now. Okay, cool. Alrighty, so hopefully I hopefully you guys heard at least a little bit of that. But basically, what's going on now is when we put an equal sign, or I'll just go through it one more time. If we put an equal sign in our smart dimension, then it'll allow us to select specific global variables. Really, still no sound. Are there other people who are still having that issue right now and can't hear me?
I can hear you just fine.
Okay.
You might have to type that in because
Yeah.
if they can't hear you, then they wouldn't know that you're asking them.
Yeah, that's what we just did. Discord's being a pain today, it sounds like. I'll wait just a moment. Perfect. All right. Well, hopefully, if anybody is still having issues, then they can just refresh or Control R, and then they'll get that situated. Okay. Technical difficulties, but I think we should be good now. So the main thing, hopefully, I can go back at least far enough such that you guys understand what I'm getting at here. So I'll just redimension this rectangle that we have here. Um, so essentially, if we are smart dimensioning specific lines or curves, uh, obviously it's just going to first initially give us what that measurement actually is. However, similar to in the global variables tab, if you make an equal sign, it'll give you some other options, just like how it did when it was asking you to assign a variable, or rather a value or an equation. So the first thing on the list for your smart dimension now should be global variables. So we can now select that and it'll automatically populate the smart dimensions with that specific variable. You don't have to do it this way if you want, if you know what specific variable you want to assign here. You don't necessarily have to select it from the dropdown. You just need to ensure that that variable is in quotes, kind of like how it is for some other coding syntax. You need to make it very specific what you want. And then beyond that, you can just create other relations. So I can say, well, I have this a that's in quotes here, and then I'm going to multiply it by 5. And that'll designate it to be whatever the heck the a value is, times a constant value of 5, which in this case is just going to be 100. And similarly, if I did the same thing for the other side, it's already smart dimension to 40, but if I select the A and then I multiply it by 2, well then it'll ensure that it is 40 in a parametric sense. Or rather in a variable sense. So now, if I actually changed any one of those values, I mean, just like what you would probably expect, if I set a to be 10 instead of 20, well, then both of these values are going to be cut in half. Scale-wise, it'll be exactly the same, but in terms of it being identical, it will be about half the size or half the respective measurements. And then the other measurements that it gives us, or rather the other A measurement, one of the other A measurement that it gives us, is that we have 3/2 of A, which should end up being 30. But we'll still do this by way of using an extrude. So the cool thing about this is that for the most part, most functions can also be integrated in with a good handful of features. There are some that don't really work out too nicely, but it really doesn't hurt to try. Anytime you do note that there might be some sort of variable that you would like to integrate in with an equation, just slap in an equal sign and see if it works. So I can put equals, it'll allow me to select my global variable a, and then I'm going to multiply it by 3 divided by 2. This is actually a much better example because I'm pretty sure you guys can actually see it this time. And I'll hit millimeters. Um, and just like before, if I hit this sigma, it'll toggle between what the value is and what the equation is. So this is a good way to get an idea of, I mean, is this the value that I really want it to be? Or perhaps if I do change what the A value is supposed to be, will I get exactly what it should be? And then when we hit select, we'll actually have our shape. So, I mean, you can obviously demonstrate this. I mean, if I go into the Evaluate tab and check the mass properties, currently it tells me that I have a mass of 120 grams. However, let's say I changed my A value to 25 instead. So all I did was I went back to Manage Equations, I changed the 20 to a 25, and then I hit OK. So if you do that, you should see, and you probably saw on your end as well, that uh, this rectangular prism did get larger. And we can verify this when I check the mass properties now. It's at 234.38. So it's, I mean, what, it like doubled in mass because of that times is that 5 millimeter increase in all the given directions, or the respective directions. And I went back too far, so I will just extrude that one more time. I'll make sure that that is an A times 3/2 millimeters. And now I want to start adding the holes that are given in the image. So these ones here are also variables as well. So it tells us that our, at least from one of those edges there, or like two of those sides, it's B by B. So it's 10 millimeters by 10 millimeters away from that respective edge that's over on that like top left-hand corner. So what we'll do, and it tells us that it is a Seabore number 5 binding head machine screw. So let's see if I can remember that. Likely won't be able to, but you know, so it goes. I'll make sure that we have a correct placement, and before we even do that, we can smart dimension this. And very similar to what we did before, since we're smart dimensioning it, I can still put equals and then select my global variable as B and hit enter. You'll see that now it's has that sigma next to it with a measurement of 10. Very similarly, I'm going to do the same thing from the other edge. So do that, set it to be equal to B, hit enter, and now it's in the appropriate location. And I think if I'm actually correct, I might have cheated here a little bit. Okay, yeah, since I made this the other night, some of these measurements are already here. I'm sorry, I'm a cheater. But we have a C bore or counter bore. It is a standard ANSI inch, binding head screw, size is number 5. Fit is close, doesn't really matter. We're not really too concerned about that unless we're actually applying screws. And it has a 10 millimeter depth from depth to tip, or down to the tip. So I'll wait just a second for you guys to take a look at that and make sure if you are following along, you have all those things labeled there. And when we hit OK on this, we'll have our screw hole as we might expect it. We now know, I mean, if we go back into that sketch, we'll see that these things here are, they still have the sigma there, so nothing has fundamentally changed. So we still note that if we ever change the B measurement, the location of this will also change. So next, well, I mean, just like how I mean, I wouldn't necessarily want to the uh, in the whole wizard to create each and every one of these. Not to say that it would be difficult to do, but just for proof of concept, I'm going to do a pattern. And we haven't done patterns too much lately, but that's okay. Even better then. But as I said, proof of concept that you can use these variables in something like patterns as well. Just about anything that has some sort of a spacing or distance measurement will allow you to use patterns. So it tells us that the spacing between each individual hole along the long axis is going to be, what is that measurement one more time? C. So we'll put in equals C from that drop-down menu, and we'll bump it up by one more. That looks pretty darn good. And then we'll also select the other perpendicular edge, and pretty much just as what you would expect. Now we want a measurement of A in this one instead, so we'll go back here. We'll say that instead this has to equal A, and I'm fairly certain if you just hit that letter on your keyboard, then it should show up with the variable if it is applicable. So you can just select that from the drop down. If I just said, screw it, I don't want to go through the hassle of going in the little menu, which can be a bit fidgety sometimes, and then selecting the letter. If you just set equals A or equals B or equals C or equals whatever variable you have assigned there, then it will, generally speaking, show up with the appropriate one. And we want two instances of this going in the opposite direction. And now we can hit OK. I can't remember what the material I signed was, which was no material. Awesome. But this, by and large, is our geometry here. So For the most part, this was just a reasonable proof of concept of using both equations and using variables. Now, here's something that's actually kind of cool. Let's go back into our Manage Equations tab. So right click and then hit Manage Equations on that equations folder. We're actually going to see some extra stuff that's populated here now, specifically in the equations drop down. And all of these equations here are going to be the ones that we utilized in our original, or rather when we were just dimensioning this in general. So what's nice is that we can also add equations from this tab as well. I believe I go through it a little bit in the PowerPoint, but the main thing here is that we actually are able to just select a specific sketch and then select the dimension or a respective dimension on that sketch, and then assign appropriate equations to that. So if we notice that maybe a specific equation or a specific measurement should be 5a, well, we can actually assign it from this window. We don't necessarily have to assign it from the Smart Dimensioning tab or Smart Dimensioning uh, window itself when we're actually dimensioning a sketch itself. So because the equations are set, you do not need to define relations. Um, I believe the answer to your question is yes. So the only reason I'm a little bit hesitant to put it in that manner is because we can distinguish between relations that are in a sketch itself, like saying that 2 points or 2 lines might be horizontal to each other, or perhaps equal to each other, or perpendicular versus parallel to each other. Um, but I believe sort of what you might be getting at there is if I change any of the variables that are here, it will automatically change any relevant equations that that variable exists in. So if yours, I mean, if yours might not look like mine in terms of that equations, global variables, and dimensions window, I have technically um, four equations that are dependent upon my a variable. If I changed my a variable to say 25, the what all four of those equations would evaluate to would be dependent upon that 25 now as opposed to 20. So that a times 5, if I changed it from a 20 to a 25, is going to increase by 25. So we'll have a measurement of 125 instead of 100, or we'll have a measurement of 60 instead of, or not 60 actually, we would have a measurement of 75 instead of 40. So things will change automatically depending upon what sort of adjustments you might specifically do to to your global variables. So it is something to sort of keep in mind when you're working on these sorts of things. Occasionally, you might have to ask yourself if you are dealing with a part that could be parameterized. Um, do I want certain things to move? Or rather, do I want certain measurements to be dependent upon other measurements? So those are questions that you might need to ask yourself depending upon what the part is or what the engineering drawing calls for. So that wraps it up with regard to equations and 3D drawings. So now we're actually going to, at least what I believe, uh, because I kind of enjoy this stuff, and I think a lot of you guys who are at least either just now getting into engineering or have been in engineering for a while, either one, um, you'll probably enjoy this sort of stuff. So we're actually going to start talking about simulations now. So a lot of the stuff that I'm going to go through right now is heavily based upon the PowerPoint. So I'm not going to be doing a whole lot on SolidWorks. So I'll let you know when we can tune back into SolidWorks, but by and large, I'm not going to be touching it for the next like 10, 15 minutes or so, possibly. So now we're going to be talking about simulations. So the most basic simulation that we can really do here for this class would probably just be like a static simulation. So some of you probably have taken a statics class, some of you perhaps not, totally fine. Just the general background behind statics is that it's a branch of mechanics wherein we have rigid bodies, and we want to make sure that all of those rigid bodies are in perfect equilibrium. So this draws a lot on Newton's law of F equals ma. Um, I mean, if you think in a very basic sense that we have some forces that are going on in our assembly or in our component or in whatever realistic scenario we might be looking at, but generally speaking, things that are in a static equilibrium aren't moving. Well, things that aren't moving don't have acceleration. So that means that the acceleration is zero. So that means that we can just say, well, who cares about the ma portion? It's just zero. So we want to ensure that all of our forces in any given direction are equal to zero. This also means that any moments that we have as well are equal to zero. And if you haven't taken statics, that's okay. We're not going to go too deep into any of that unless you want more information about it. This is more about kind of the fun stuff of actually performing these simulations and getting kind of a cool idea of how the results actually flow. And I know I talk a little bit about it in the PowerPoint, but basically we would end up going to our simulations tab and hitting new study. But I'd rather do that at the end when we actually get to the actual the fun stuff of performing a simulation on this part that we just created here. So in terms of simulations, there's some very basic things we need to know. First and foremost, why the heck do we even care about simulations in the first place? And most of you probably already have a pretty good idea about that, but I mean, obviously deriving from the word itself, sometimes we don't want to actually just say, well, let's just send it and see what happens. That's generally speaking not good for engineering, especially if you're not doing any sort of testing whatsoever behind it. So it's just a good way to be able to recreate behavior or any sort of uh, anything that this part could possibly do. And that's not to say that the simulation will be an end all be all. There are times where you need to use engineering judgment to look at something and say, that doesn't sound right, or that doesn't seem right. So simulations are not an end all be all, but they're a very good way of getting a a robust understanding of what could possibly happen given the model that you have. You always want to make sure, especially with a simulation, that you're sort of overestimating what could happen. Because then in that situation, if the worst possible case does happen, if you've over prepared, well, then you know that that's not going to be the case. You know that that catastrophic failure or say the ultimate strength is reached or anything of the sort in that instance doesn't actually happen. So there's a couple things that will pop up when we choose a static simulation. And these are very basic things that you will generally see in simulations in general. So by and large, you're always going to want to be keeping the majority of these things in your mind when you're doing just about any sort of simulation, not just a static simulation. And these things are going to be the geometry and the material, which generally speaking go hand in hand. Contacts or connections is labeled as connections in SolidWorks. Some other softwares call them contacts or contact definitions. And this is really just dependent upon whether or not you have multiple components that are already within your part. So contacts or connections is really only going to be applicable if you have things that are assemblies. So contacts are going to be instances where maybe you have some sort of roughness or friction that is happening between two faces. Perhaps you might not have a nice clean contact between those two faces, so you need to account for those sorts of things, such as adding specific um, coefficients of friction and paying attention to those factors. Uh, Probably the most new thing here on this list would be a mesh. And then we also have boundary conditions and fixtures, as well as loads. Boundary conditions or fixtures is just a way of determining whether certain aspects of the geometry are supposed to not move entirely, or perhaps maybe they are, how would you put it? They're not supposed to move, but maybe they move in a very understood manner. Um, and this will a lot of these sorts of fixture, the ideas of boundary conditions and fixtures do come up in statics in general, hence why they are here as well, but they're in most simulations as well. So having no boundary conditions whatsoever or no fixtures whatsoever is usually setting yourself up for failure. You need to have something that is there because it's like thinking about perhaps a calculus problem where you don't actually know what the uh, beginning and end of your integral is. Or perhaps like for an integral. If you don't know those things, well, yeah, you can find a definite integral, or rather an indefinite integral, but you can't really solve it for a specific region unless you're told to do so. And then for loads, we have any number of different kind of loads. So we have mechanical loads, which would be things like forces, point loads, pressure forces, which are going to be about a specific face. We can have thermal loads, and I'll talk a little bit more about all these things that I just described here on this next slide. So some of the more unfamiliar ones are kind of going to be, like I said, contacts or connections, which are just going to be regions where components or faces of components will meet. And we do need to create some sort of definition between those regions there. So this could be saying, well, they might be frictionless just to save on computational power or effort. They could be frictional, which might ensure that we have a more realistic simulation, but it could add a bit more processing power because it's solving different equations, or rather, it's integrating in another variable that it needs to keep in mind. So a mesh is something that is more specific to the realm of finite element analysis, or FEA. Some of you who may have done some simulation-based stuff or had very loose understanding of SolidWorks before coming into this class probably have some idea of what a mesh is. But it's basically a way of taking kind of that solid geometry that we already have when we create our components and breaking them down into very, very simple parts, or more simple uh, geometries in that manner. So generally, we like these to be a bit smaller, or we like these to be small because then we can get a more accurate representation of what's going on. Additionally, we have our boundary conditions, which, as I said, these are just going to, generally speaking, be regions of interest, places where there's a very specific thing going on. So you could, in some instance, say, well, hey, if I have a boundary condition for a thermal problem or a problem that integrates in temperature, there might be some sort of surface that is at constant temperature. That could be considered a boundary condition, or perhaps it doesn't even stay at a constant temperature, but maybe it has a specific temperature at a given time. Perhaps at time zero, it's STP, it's standard temperature and pressure, so it's like around 23 degrees Celsius, something of the sort there. And similarly, these sorts of boundary conditions can take on different forms. You could have a fixed boundary condition, which means that surface has 0 degrees of freedom that are free. It can't move, it has no ability to translate, and it has no ability to rotate. So that's an important thing to keep in mind. Certain things like roller supports or hinges, well, those do have certain degrees of freedom that are restricted, but it has other ones that are not restricted, ones that it can move in. So those are important things to keep in mind. We're not really going to be going through too much with regard to roller supports or hinges because that gets into a lot of nitty gritty stuff that if you haven't really talked or gone through statics, it'll be a bit of an uphill battle, and I don't want to do that to you guys. Um, and lastly, loads. So kind of like what I described before, but loads are going to be forces or pressures or torques or temperatures, things that can be applied to this geometry to better simulate what is actually or realistically supposed to happen. Furthermore, I talk a little bit about fixtures, and this is just going into actually how to apply some of these things here to our model. So yeah, I'll come back to mesh, and let's actually just very ba let's create some of the basic aspects of our simulation here. So kind of like what I talk a little bit about in the PowerPoint, but if we go back to our SolidWorks, in the command bar, kind of in the middle of it, we should see something that's labeled as simulations. When we click on this, the only option that we're allowed to click is a new study. So we'll select a new study, and we will just start off with a basic static simulation. We're not going to go really into any of these other ones because I haven't really played around with them too much, so I don't know how they function in SolidWorks as well as I do in some other softwares. So right now, this looks pretty similar to what I have in the PowerPoint, but let's kind of break down these things. This very first one here in that dropdown is going to be both the geometry and the material. So currently it doesn't have a material assigned because I didn't assign one before, but we can still assign one from this tab. So if you right click on that very first option, we should get it as though I was selecting that material not specified tab. And I want to ensure that there is a material here. So we'll hit apply/edit material, and I think I set it to be alloy steel, if I'm not mistaken. Now I need to go back and check. Yes, alloy steel. I didn't say it in the PowerPoint very specific, but that's what it should be. So you can either type it in, or it should be kind of near the top of the list, or rather middle of the steel list. And then just hit apply, so we should have this kind of slightly lighter color now. And it is assigned. We can see that here it's specifying an alloy steel. We don't need to select it or do anything else. We don't need to mess around with connections because, as we said before, this doesn't have any connections to other parts. Or really any self connections or anything like that that we need to take into account. So the next part is that we're now going to go into fixtures. So if you right click on fixtures, you should see something that says fixtures advisor. This is kind of a better way of SolidWorks does a good job at kind of guiding you how to use simulations. But if we already have a good idea as to what we want, or if we just want to directly go into the menu, from that right click menu, we can just hit fixed geometry. So now if you sort of just mouse over the different faces, you should see these green cones that show up. And those green cones are just sort of indicating regions that could be fixed. So if I selected this face here, it would actually fix that face. So that's not necessarily what we want. I want to fix this face over here, almost like from where our orthogonal view is, or isometric, excuse me. So this face that we can see, I believe it's the right view of uh, our geometry here. I want to fix this, so I'll just select it. And the blue face as well as the green cones that are not disappearing now is an indicator that that region is fixed. So I'll hit select. I only want to fix that specific region right there. Simulation is not detailed enough. I have the dancing cube. It is glitching. Going to refresh. Dancing cube. Simulation is not detailed enough. Is that happening when you try to go to a new study? If anything, I can just upload this specific part as well. And hopefully that should work. I might just do that anyway. Here, that's what I'm gonna do. Man, all the technical issues today are lovely. It is this one. If you guys want, you should be able to just directly download the part right from there. And then you should be able to open it up. But I will give everybody a second if they want to just take that one. I'm fairly certain that's the correct one. I haven't really changed anything. But God only knows. Let me open it up just to double check. Dang it, it already has a static simulation in there. That's fine. We can always create a new one. Or you guys can, at least. You would just want to make sure you're in the model view and then hit new study if you're following along with this one that I just uploaded. To make a new simulation, Miranda?
Yes, please.
Okay, yeah. So in order to do that, now that I just uploaded this one specifically, all you would have to do is if you go to the simulation tab, which should be in the middle of the command bar, the first option, or rather the only option that you can select, should be new study. So there's already a static simulation in there anyway, but we're just going to create a new one. So when you hit new study, it should appear with this list that's on the left-hand side with all the different types of study that we can do. We're not going for anything specific. We're just going to do a very basic static simulation, which should already be selected first and foremost, because it's kind of depressed into the page already, and then we can just hit OK. And then we should be able to get back to pretty much this exact same uh, layout. We'll just create the fixtures and the loads one more time. So hopefully everybody is good now. But basically what we would really want to do next is we're just going to ensure that we have that fixture that is on one side, the right view of our geometry. And now if we mouse over it, we can see that there is a fixed region. You can add multiple fixed regions either at once, in different, either separately. So kind of similar to how if you are adding like a fillet to something, you can either create all the fillets in one, or you can just make several fillets if you kind of want to break it apart a little bit. And then the next thing that we do want to add is a load. So as it stands right now, um, I wouldn't even say that this is a cantilever. And the reason for that is because there's actually no gravity or any sort of weight force that's being applied to this right now. Think of this as kind of just being in space right now. It has no alternative forces or extra forces that are being applied. It's in a vacuum. So we can go to our external load. So if we right click on external loads, the very first option should be force. And you'll probably see that there's tons of other options there as well. So there's options to add torques, pressures, gravity, temperature, like I mentioned. So far more things than even I had mentioned in the very first place. And very similar to what we did, rather than putting it on the same end that we had fixed, which would effectively be meaningless, it wouldn't do anything, we want to put it on the very opposite end of this geometry. So now we have these purple arrows, and if we select them there, now we kind of have this thing where it's as if you're basically pushing a brick against a wall. The wall is going to prevent the brick from moving, but you still have a force that is being applied to one side of this geometry. And a 1 Newton force is effectively nothing, so we're going to bump that up. We want to see this thing deform a little bit. So I believe I set it to be 150 instead of just 1 Newton. And we can see that now it has a force value of 150 Newtons. We can reverse the direction, so instead it would be basically pulling this object instead of compressing it. Also, what we could do is, if I wanted to put this in shear, I would select the direction, and I would select just a direction that I would want it to be shearing. And then I can essentially get a force that is being applied to this face at every point on this face that is basically applied completely parallel to the face. But I want it to be normal to the face, and I want it to maintain 150 Newton force. We can obviously do another static study and basically see what happens if I had a shear force that was applied to this. So we'll hit select. So now we have 100 Newton or 150 Newton force on one side. We have a fixture on the other side. And the very last thing that is going to take up a little bit of time is talking about a mesh. So if we're looking at, I mean, just very basic, if we're looking at the PowerPoint, I talk a little bit about the mesh, but the important thing to kind of take away from the mesh is that we're really just representing this geometry as a much finer group of smaller geometries here. Uh, there are some very fundamental things that you need to be aware of. So if we're dealing with a simulation here, we typically like smaller mesh elements. Two things that you typically hear when you're dealing with meshes are elements and nodes. Elements are just the number of like tiny little geometries that you have, polyhedrons that you have, and nodes are just the places where all of those little polyhedrons will meet each other. So some fundamental concepts that you really need to be aware of if you are doing simulations. Um, if you have smaller numbers of elements, or rather fewer elements on a geometry, unless it's comparable to the size of the geometry, you're not going to get very reliable results. And the best way that I could, might be a kind of stupid example, but the best way that I could think of phrasing it would be to think of, say, a bag of sand, or even think about the geometry that we have here as being a container that holds the sand in it. If you have something like that versus something that is, say, a bag of marbles, well, the bag of sand is going to be able to move much easier. It's going to be far more malleable when you create these sorts of deformations, or you add these sorts of loads to your geometry. Um, but does that necessarily always mean that we want to have the finest mesh possible, the smallest components possible? And I mean, why would I be asking this question if not to say no? We don't always want to have very fine elements. And the reason for this is because, think about it, if you're putting tiny little geometries inside of a larger geometry, that just means that more of these smaller elements are going to be able to fit in there, which requires that much more computational processing power. I mean, it's going to stress out the CPU of your machine that much more, because you're literally solving matrices. You're solving very large matrices to figure out a numerical solution in order to create this deformed or stressed geometry. So just because a finer mesh might produce better results doesn't mean we always want to do it. Similarly, increasing the mesh size, or rather the mesh density, if you will. And when I say mesh density, I just mean that if you increase the mesh density, you have more mesh elements inside of your object. That just means that there's the possibility for there to be a point where you're just getting diminishing returns. You're not actually getting better results, and you can always compare those results. You can look at it and you can say, okay, well, I did one simulation which had, say, 20,000 elements perhaps, and I got some results. And then I said, okay, well, maybe let's try to do it with 30,000 elements. So I decrease the size of my elements, but maybe the values that I get are, I mean, within a tolerance of like a thousandth or a 10,000th, or even smaller than that. It's kind of up to you. I mean, using engineering judgment to look at that and say, okay, well, is this acceptable? I mean, maybe if you're in like the airline industry, those sorts of finer and finer and finer measurements could perhaps be required for your intents and purposes. Uh, Perhaps for a larger scale project, or maybe doing any sort of structural analysis, or uh, uh, civil engineering, that might be necessary to do, but there are times where it might not be required to be that specific with how fine your mesh is. And clearly, if it's taking more computational power, it's going to take more time. Um, as a frame of reference, and I know that something that we're seeing here is very different than some of the work that I've done. I haven't really talked about it too much, but um, some of the meshes that I've dealt with have been on the order of like 1 million elements, or even upward of like as little as like 500,000 elements. And for a beefy computer, that can still take hours to run or hours to create that mesh. And if it takes hours to create that mesh, just think about how much time it's going to take to create or produce a coherent result or results. So we want to make sure that any mesh that we put forward is not going to be too fine, but it's also not going to be too rough as well. And SolidWorks actually does a fairly good job at representing this, with kind of how it does its default options. So if we right click on mesh and then we hit create mesh, it should be third option from the top, we should get a new menu that looks like this. I'm not really sure how the mesh quality tab works, but the important thing that we're going to want to note is both this very first part, which says mesh density, as well as the mesh parameters. Mesh parameters just gives you a better idea as to the fineness of your mesh. Obviously, I can move this, and if you're looking at that kind of that number down at the bottom, it's it's increasing or decreasing. So what the heck even are these two? One of them is a global size, which is just going to be the default size of, I guess you could say like an edge length of each of those independent elements. And this is also a tolerance. So right now, I could have a mesh element that is around 7.4, 7.5 millimeters, but I could also have one that is about 7.1 millimeters, or perhaps one that's closer to 7.7 or 7.9. So it's basically saying that I have a general mesh element size of around 7.5 millimeters plus or minus zero point 0.3 millimeters to go along with it, because we're not always going to be able to create a mesh where you can fit an exact number of those elements of a given size into this geometry, especially when you're dealing with curved surfaces and things that are very odd shapes. Sometimes SolidWorks or other CAD softwares need to use their engineering judgment, if you will, to create things that are appropriate. So here we'll go for something that's a little bit smaller, and I'm actually just going to use not even so much the sliders, but use specific measurements. So I'm going to say that we want an element size of about 4 millimeters with a tolerance of zero point 0.2, so a fifth of a millimeter. And then we don't really need to do any sort of advanced options. I don't even really know too much about how these work. And some of these are other options about how the mesh is formed. But we're not really too concerned about any of that. So when we hit select, this should generate our mesh. So don't be alarmed. What'll happen is you'll get a little pop-up. It'll kind of show you the processing power required to finish it. If it is taking too long to do, just create a coarser mesh. And that'll actually be good if it does take a bit too much time, because that just means that between what I do and what you do, we might be able to compare results. Obviously, I can just create another static simulation and compare results with my own uh, varying mesh, but could be something interesting if we want to do that. So if I hit OK, it'll generate the mesh. I think it did it fairly quickly. And now we can see our elements. So each one of these guys right here is considered an element. So it's not actually just a flat surface. I'm fairly certain if I cut this in half a little bit, it will produce absolutely nothing. Excellent. So that didn't work out how I thought it was going to. I'm a little bit jaded. Some other softwares that I use do that. But that's okay. We can basically see that we have a bunch of elements here now that are creating the mesh of our geometry. And the final thing that we need to do just in order to produce our results here would just be to run this. So if we, there's two ways of doing it. I believe if you right click on mesh again, you could select mesh and run, but we've already meshed it, so we can select this run this study button. It should be right above, just to slightly to the left of where the simulation tab is. And it might take a couple of seconds. Hopefully it doesn't take too long to run. um, to get through this. So that didn't take too long for me. Hopefully it doesn't take too long for you guys as well. I know not everybody has um, too powerful a computer, so hopefully, like I said before, use your best judgment. Even with my computer, which I would say is a bit hefty, I created a couple meshes last night, or I was trying to create a couple meshes last night, and SolidWorks just didn't budge, which is an indicator to me that it was basically saying, you're going to be waiting here for about a half hour, bud, if you really are super intent on creating this mesh. Um, but whether or not you do have your own results to look at, or if yours is taking a little bit too long, we can take a look at what's going on here. So this is pretty. At least I think it is. But now the color has changed according to uh, our slider here, or our diagram here, and it's basically just showing us the regions that have very little stress going on and the regions of highest stress. And the nice thing about SolidWorks as well is that it provides to us the yield strength of the object itself, something that I'm a little bit jealous of that some other softwares actually don't do, surprisingly enough. But here it's telling us that the yield strength of this alloy steel is 6.2 times 10 to the 8th newtons per meter squared, or megapascals of pressure. Or we could have it in this instance where we're looking at the very top here, which is indicating just shy of 4 times 10 to the 5th megapascals. So this is good. I mean, I don't know why the heck you would want something with about, 12 screw holes in it that you're compressing against a wall, but there are certain times where you might have parts that you need to do these sorts of analysis. So I'm fairly certain the majority of you guys have not taken engineering design, but usually curved objects like this, or holes, um, the how should I phrase it? The direction that is perpendicular to the force, whether it be pushing or pulling, compression or tension, is going to be a region of higher stress. So we can see that this region right here is incurring higher stress, as well as pretty much all of the regions that are kind of perpendicular to that force. Um, and then we can also kind of see, like, almost say the wireframe of our original model if we mouse over it. Uh, all this is really just encompassed within the stress uh, of this uh, of this object here. So if I want, I would just double click on displacement, and now it's going to show me the displacement results. So it's showing that over here in blue, we have things that are of the order of 1 times 10 to the negative 30th, which I am uh, within reasonable certainty is smaller than an atom. So keep in mind, these are numerical simulations, so it is calculating a number here. It's not calculating, or it's not using logic. So that's where you guys need to kind of step in and say, if you add that to a paper or something like that, you might have some people furrowing their brow and saying, okay, well, it's zero. Let's let's be real here. It's basically zero displacement, and it displaces on an order of just shy of 7 times 10 to the negative fifth millimeters, which is also quite small, ridiculously small as well. So we could obviously ramp this force up and see what happens. Obviously, in an instance like that, we would get a greater stress value. We would get more displacement out of it. We can also take a look at the strain and kind of see what's going on here. This is the one thing that I'm not a huge fan of with SolidWorks, is that it seems like unless you make your mesh ridiculously fine, you're still going to get these very large looking uh, geometry, like two-dimensional geometry, where uh, all of those faces were kind of those mesh elements. If I go back to the mesh, I think it should show it. I need to find a way. Oh, right there, show mesh. So if we look at our mesh, if you right click on it, it should be near the bottom to either show or hide the mesh. Then we can basically see that that's the general shape and consistency of those meshing elements on the surface of this mesh. So if I go back to strain, then I can pretty much see that they are deforming in some manner, and there are regions of higher strain or engineering strain than others. Um, and we can pretty much dissect this and take a look at it in any manner. I think you can take a cross section still. No? I'm a little bit salty about that, though. That you can't take internal cross sections, or maybe you can. It's just not very intuitive. I'll have to look into that. But there's other plots that you can add to this as well. If you right-click on results, we'll see things like adding factors of safety. So factors of safety are just reasonably, so let me see. Yeah, all bodies. Factor of safety is just a way to kind of determine regions of your part which I guess you could say, are in compliance with the yield strength. So if I remember correctly, I believe it's something to do with like the stress level at a given point, um, dividing whatever like the yield strength is. It's either the yield strength or the ultimate strength. I can't think of it off the top of my head. And this is generally given on sort of a scale like this. So we can see that there are some regions where for lack of a better term, they're a bit sketchier than others. So kind of in line with all of these holes, just because we are compressing it and there is material and then an opening, material and then an opening, material and then an opening. Whereas if you're looking at some of the uniform regions, there's really not that outlook on it. If we want, we can pretty much create uh, other simulations based upon this as well. So, I mean, obviously this was a fairly simplistic simulation. If we want, I could just, heck, I'm gonna do this. I'm gonna see if can I duplicate this? That's kind of stupid, I can't duplicate it. I'll just do a new study and I'll just kind of show you guys. You don't have to necessarily do it if you want, but it's just a cool little thing to look at. So in this instance, I'm going to say, all right, it's still alloy steel. I want to uh, do a fixture on this same face. I'm going to hit OK, and instead I'll still do a force, only in this case I'm going to make it a bit larger. I'm going to make it 1,000 newtons, and I'm going to have to re-input that. But I'm going to make it a shear force. So I'm going to do like 1,000 Newton shear force, or a kilonewton in this case. So I have this here now, and I'll mesh it one more time. I'll mesh it and run, or rather, let me just see what the mesh properties are. Okay, so it didn't use the proper mesh properties, so I'll just set that to 4 again. And that's 0.2, so that all works out. And then I'm going to run this guy, because I want to see what the heck it looks like, and hopefully it doesn't take too long. Okay, cool. Get out of here. There we go. So kind of like what you would expect, we're going to get something that is more like a cantilever now. We have some sort of load that is being applied at the very end of this geometry, and not much stress is really going to occur at the very end here, where that shear force was, but we are going to get more shear force, or rather more stress, at regions closer to the fixed point, or the fixed region. So we can see here, we have less stress that's happening in those screw holes that are closer to the shear region, but when we get right up next to our boundary conditions, we can see that it's actually pretty egregious. If we compare these values here to the stress values that we saw here, it's literally an order of magnitude greater, um, which just means it's that much closer to yielding at this point. So those are things that you would want to kind of take into consideration. Same thing with displacement. It's kind of a similar diagram, only now it's being moved downward. Similar with strain, only strain is going to look uh, like this, just because in this instance, this is moving, or rather this face is moving fairly in a fairly uniform manner. However, you could imagine that you have, like, say, how could I put it? Almost like putty or Play-Doh. If you're holding one side of like the Play-Doh or putty, and then you're grabbing the other side, but then you're pulling it. This region over here is currently in tension, so it's experiencing that much more strain than regions over here, which are just kind of going with the flow. That about wraps it up for all the stuff that I wanted to discuss, at least with regard to simulations. Um, I'm not going to test on any of this stuff here, so I'm not going to ask you guys to perform any simulations either on the exam or for your final project unless you really, really want to. Uh, I mean, I guess maybe if you guys wanted to do, like, say, a static simulation on one of the models that I give you guys, then I could perhaps do something like that, or you could do that. I might add like a little bit of like an extra credit thing to the end of the project, perhaps. Uh, but aside from that, that's really about all I had. The only other thing that a couple people had requested was just to kind of reiterate some stuff about mates with respect to uh, assemblies. And then, I mean, I feel like really the only thing to kind of reiterate there is just to say that, I mean, I already had this specific slide on the PowerPoint that talked about mates, but just keeping in mind some very basic tips on mating parts together, such as like using common mates or a common mating reference, making sure that you're not mating things in loops or creating any sort of circular dependencies. And then the only other thing after that was I just described a little bit about like very specific, like what you can expect to see when you mate parts together. So in instances where you have edge mates, typically speaking, you're only going to, or rather, you will restrict 2 translational degrees of freedom, but you're not going to restrict much in the way of the rotational degrees of freedom. I mean, you will be able to restrict two, 2 rotational degrees of freedom, I believe. Uh, but you won't restrict everything. Similarly, with face mates, you'll be able to restrict 2 rotational and 1 translational, but not much else, because those faces that are coincident to each other are going to basically always be coplanar to each other. Say if you're doing like a, or rather, let's see, if you want to even be more specific with regard to mating components together, usually you're going to want to have some combination of face mates or edge mates that are not collinear to each other. So I guess the best way is that I can illustrate this. So if I flip on back to SolidWorks, um, let's see. I'm going to use this part here, and since I already have it saved, I'm just going to make an assembly out of it. And I'll just duplicate the part. Come on, open. Okay, good. A nice little pro tip, if I haven't said it already, or if anybody hasn't figured it out, if you hit Control and then left click on an object and pull away, you can duplicate it. So if you have several of a specific part in an object or in an assembly, it's a very good way of creating more of that specific part that's there. But just to illustrate some of these mates that I was just briefly talking about, let's say I have 2 edge mates here. So right now, if I hit select, well then this can still move along that edge. But as you probably already saw, I can basically rotate very freely. I can rotate this completely around that similar axis of rotation. So I can't move it in the X direction or in the Y direction uh, as a whole part, but I can rotate it about the Z direction. Um, Perhaps I wanted to, let me delete both of these. Perhaps I wanted to do a, not an edge again, a face mate. Well now, if I mate these 2 things together, they basically are just moving right against one another, and it's super hard to see when I move it like this. If you're paying attention to the shadow, it's not actually moving further to the right or further in the X direction, it's moving upward, which is kind of stupid, but that shadow is indicating that you have something that is higher up now. If I try to do something like that, you can see that it's ridiculously high. I know I was working with another student a few nights ago, and I was very confused as to why that was happening, but it makes complete sense now. It's literally just moving in plane. Those two faces are technically in the same plane, but it's just moving in that plane. So those faces are coplanar to each other. Um, Now, edge mates are pretty nice if you do have similar figures to each other or similar components to each other, because this goes along with what I was just saying a moment ago. If I place these two edge mates, or this edge and this edge, that's definitely not what I wanted you to do. There we go. Then now I have something similar to what I had before. It moves up and down, but it's still going to rotate. However, if I choose an edge that is orthogonal to both of those and hit enter, now these are totally fully defined because it can't move around this axis and it can't move around this axis here as well. So kind of restricting both of those two rotational degrees of freedom actually does a lot for the translational as well. So that's a good way to be able to mate parts together that might be butted up right next to each other without really having to uh, I guess for lack of a better term, like over define the hell out of it, or just create more mates that are just totally unnecessary or not needed in any way. Um, I know some people also had this issue with the uh, what was it? With the yoke and guide assembly, and I think I figured out why this was happening. So I'm actually just going to create another mate here as well, and I'm going to say that, or another one of these same bricks here, to kind of simulate it as best I can. So I want to say that these two here are parallel. Okay. And then these two here are also parallel to each other, which means now it should really only move back and forth. And I wonder, can this move down? Yes, it can. Better yet, now that I think about it, I'm just going to turn those into edge mates. So edge mates are nice just because by virtue of being an edge, they are far easier to kind of restrict. So I'm just going to make sure that both of those edges are parallel to each other. So these ones are parallel to each other. And then maybe I'll create some extra parallels as well, something like that. And then something like that. So they're kind of on the same plane. I don't really want to go too crazy with this. I just want to ensure that they're, for the most part, in the same region, and I can't rotate this at all, which is good. And then I'm actually going to fix this part. So I'm going to fix that. Because I'm pretty much saying that I want this guy to move between these two here. So the first thing I'm going to do is actually figure out what the heck this distance even is. So it's a pretty gross distance. It's 127.84, which is fine. And I'm going to add some limit distances to some of this stuff. So I'll say you and you have a limit distance. It could either be a minimum of 0 or a maximum of, oh gosh, I don't know, 128, I think it was 127.8, 7.8, 84, and I have no idea what the smaller value was. I'm just going to set it as that for a second, but I want to figure out what that's 100 millimeters. Okay, so basically this should only move about, like I would say like 27 millimeters between these two things. Why are these? Oh, I see what's going on. Since they're fixed, they're not actually going to move. You know what? I got a better way of doing this now that I think about it. Maybe at least. Not like that though. I should have just stuck with the other option. That's fine. And then I'll just make sure that these are coincident to each other. And that these are coincident as well. And then I'll see if I can do that again. You and you. Mate those guys. You and you. Mate those guys together. And then I'm gonna see if I can do some funny business here. Good enough, honestly. I'm just gonna fix that now. And then these I want to suppress. This one too. Okay, so now that can move between the two parts that are there. It should be able to at least. Oh God, I want this to be parallel. These two to be parallel. I really should just use the yoke. Okay, this is failing. I'm just going to open up that yoke assembly and show you what I mean. Right here. Okay, so this is an assembly that we had earlier in the semester, just a few weeks ago. So this is my model here. So how I currently have it right now is I have a distance of 57 set up between the face of the yoke and this side of the screw here. However, if I actually add another limit distance that is essentially identical to the other one, unfortunately we're going to see some stuff that we don't necessarily want. We're going to end up, come on, cooperate. There we go. If I do another limit distance, and I do it between this face and this face, it's still going to be 0, and it'll be a max of 57. When I hit OK now, and when I leave this, that's strange. I don't know why. I thought the limit distances would not cooperate with each other. They kind of don't in their own manner, just because when I pull on that side there, it's very rigid. When I pull over on that other side, it kind of stops prematurely. So the idea is that you want to really only have one limit distance. I don't know why it's actually still fully defined because, oh, there we go. When I rebuilt it, it actually underdefined the yoke and the adjusting pin. And that's totally because I have those two limit distances there that are basically vying for the correct measurement. So I think just really the end all be all, or the basis for what I'm getting at here, is that you don't need both of them. You only need, or you only should have, a single limit distance from a given reference point, or else then you're going to have both of these limit distances that are fighting each other to try to get a correct measurement for where the yoke and the adjusting pin should be. So yeah, so I think that's generally all that I had to discuss about at least that example, or that there. I know I had someone who had mentioned that the other day. I feel like a good handful of people probably already left, which is fine because then they'll just have to deal with things for next week. But sort of coming back to what I had mentioned regarding the exam for next week. Not mating to the base perfectly, it kept ending up being off slightly. I think So let me actually just go through some of the mates that I have here. In fact, what I could do is I could just mate this from scratch, um, or just creating multiple mates fix my issue. It could. Um, the two things to keep in mind is that you just want to make sure that your mates aren't being redundant, so you don't have something that is um, like this example here, where you're defining several things at one time, where it already knows what it's supposed to be doing. Like if I just suppressed all of these right now, and I mean obviously I have them right on the side, but I mean if we just kind of take a look at some of the mates that I made, I had a concentric mate between the whole of the yoke and the adjusting pin, which should be fairly intuitive. Um, in terms of other ones that related to the adjusting pin, I only had a distance. I didn't have a limit distance. So this is basically supposed to be fixed in this position right here, so I can't pull it out in any manner. And then the other one to keep in mind would be a parallel. And the parallel is going to be between any line or edge or axis, and the cylinder of that adjusting pin, that hollow cylinder. Some things to keep in mind would be that parallel and perpendicular can not only just be an edge, but they can also be faces and even cylindrical faces as well. Um, Nice, perfect, and pristine cylindrical faces, SolidWorks is able to interpret that not just as a cylinder, but also as an axis, and it takes that into account. So if I wanted to, if I go into this parallel, if I wanted them to now be, say, perpendicular, it's going to adjust such that this edge and the axis of this hole are now perpendicular to each other. Otherwise, I would just have it as parallel, where they're now facing the same direction. Um, in terms of other mates that I have here, um, for the yoke, I'm fairly certain I don't have too many that are here for the yoke specifically, so I'm actually going to suppress this just so that it's good. And now it moves smoothly. Um, I have one coincidence between the interface of the guide and that interface of like the yoke clamp, and then I have another face coincidence between that bottom face of the same side. I don't think it has to be for the same side, but it's good to just keep those things kind of close together. And then the top face of the inside of the guide. So if we're thinking about this in terms of degrees of freedom that are being limited, if I only have this coincident mate here, this yoke can still revolve around in that direction. And it can also move like left or right, up and down from this view here. But in conjunction with this other coincidence, it now limits the direction. In fact, it limits any translation other than translation that is going to be coplanar. Because coincidence is basically ensuring that those two faces or edges or whatever geometry you have there are kind of glued together. Or maybe not even glued together, that might be a bad word, but more so they are touching each other. They have to be right up against each other, just like how things that are coincident in a sketch are right abutted next to each other. The other things here that I have, so I mean, I know I have some other coincidence that are here, but this was really just a test, just to see if I even needed those there, which you really don't need to create those other mates on the other side as well, because it's just as restricted as this side is here. It kind of harkens back to what I said probably a couple lectures ago about how creating assemblies relies very heavily on an understanding of what your parts are. If you're unsure about the measurements of your part, it makes it very difficult to create proper relations. And those are times where you really might need to go to your evaluate tab and check out the interference detection. because there could be very, very real instances where it might not look like there's overlapping geometry, but you can't pinpoint that from just a very cursory look, but SolidWorks can. It's going to look at any of those overlapping regions and point them out with a funny sound included. There's also concentric for the screws, and I just made it such that the screws are going to be parallel to some sort of a given face. And the reason that I did this was just because it's going to make it that much easier to dimension this guide, or rather dimension the yoke. Because now I can just say, well, I know that from here to here is 77 millimeters. If I incorporate how the yoke is taking up 20 of those millimeters, well, it's really just an exercise in wholes and parts. We have a hole of 77 and we have one of our parts being 20 millimeters. That means that there's only 57 millimeters of leeway that can ever exist here. So it's just up to saying, okay, well, what's the maximum distance that this could possibly be without creating overlapping geometry? And that's really how I did it, at least in this instance. I know a couple other people use some other clever techniques, like using like some of like the width mates, which I didn't even think of, which is actually super cool. And certain instances like that are acceptable as well. They take a little bit of finesse to actually use, but they're totally reasonable. Like I said, I used a limit distance for mine, which is also a manner of doing it. Um, yeah, but the one big thing, at least kind of to your question, is try not to create too many mates such that you have redundancy, but make sure that you have enough such that everything is still going to be fully defined. Um, Anybody have any other questions about stuff?
On the red mailbox, I have a question about how you got your configurations for
Yes.
having the open lid on it. Every time I open it, it opens it on all my views, but when I close it, and I can't make it to where it doesn't update the views for the other ones.
Yeah. So I put a little note in the submission, and it's kind of hinting at exactly what you're talking about. Um, you don't just need to create one exploded view, or one configuration. So I guess if I want to illustrate that on something like this, if I go to my configurations tab, and I'm just going to ensure that this is all the way to the right side, um, I can say, all right, well, I'm going to add a configuration, and I'll just say this, just config2 or something. I don't know, something lazy. And I'll just pull this over to the other side, something that's very rudimentary. Um, well, now I'm fairly certain. I think if I, how did I do it? Yeah, adding another configuration doesn't work as well just because it's still taking on pretty much the same orientation as what's on the other one, but an exploded view will actually account for that. So even if it's just saying, well, I'm going to, let me see. This is default. I'm going to click on this config2 and I'll add an exploded view to it. And honestly, I'm really just going to move this. Ah, crap, it's going to do that. I'll just like move all of these parts to kind of like the opposite end over here, which I already said it should be 57 millimeters. There we go. And then just hit OK. And now I could say that in one of my views, the default has the yoke on the left-hand side, but for the exploded view, it's on the right-hand side. So one manner of getting kind of those differing configurations without creating like an explicit exploded view is to just make very small adjustments. For one like that, keep in mind that of where it's rotating about. So very similar to something like this that I have right here. Um, I want to make sure that that door is opening, but if I just selected these things here, assuming this could rotate, and start rotating it, it's not particularly going to rotate about the place that I want it to, which you can actually do is I'm fairly certain, it might have to just be a single object. I know you can move that center of rotation, or rather you can select the region where you want it to be rotating about. So you do want to ensure, it's right here actually, now that I think about it. It's this one right here on the side, which kind of dictates where it's rotating about. So maybe I want to rotate this pin about this inner face. So I selected this box here, and I selected the face that I wanted it to rotate, and now it's rotating completely about that cylinder, that empty cylinder. What you can do in a case for the mailbox is you would just need to say, okay, well, I want to ensure that it's rotating about the pin, the cover pin, to make sure that it's only rotating as though it were opening up. Does that kind of make sense?
Yeah, it makes sense. I
Okay.
didn't know you could select the point where it pivots.
Yeah, I didn't explain it, but there are some other options in here where you can select the region by which to rotate that object. I know that there's other probably slightly better ways of doing it as well. I think there was something that I was trying to do the other day and it worked possibly a little bit more effectively. But that is one mode of getting it to work, just creating another exploded view that has it rotated in the correct direction. So it's not even so much an exploded view as it is just kind of creating a proper configuration. I think if you do play around with the configurations as well, it could function in the way that it's supposed to. Yeah, because right now this is basically saying that default position would be on the far left, which is fine. Um, but that's a way that you could add other views to it as well. Just adding different exploded views where the geometry is technically still intact. Just rotating it about specific regions or moving it about specific regions.
Thank you.
Yeah, no worries. Anything else?
So for this week, is there like any assignments to speak of, or is there like an extra credit thing, or?
I don't have anything planned, so I mean, if you if you guys were after that, I'm sorry to tell you, I don't have anything for you. So hopefully you guys can look at this and hopefully take a breath and use it to kind of prep for the exam next week. Like I said, I did kind of want to talk a little bit about that as well, and maybe get some ideas of what you guys would desire from an exam.
Yeah, no, I'm definitely on team like not having an assignment this week. So
Okay. I I don't think you're alone in that measure, so anybody that wants the extra work can just come to me personally about it. And I'll try to think of some, I was about to say garbage, but think of something to give to you guys. But off of that note, like I said, I do want to talk a little bit about the exam as well. So in terms of the exam, like I said, I don't have any of it prepared currently, but I have it set up, or I would like to set it up such that there's two problems, one that's fairly simple, and you guys basically do it from start to finish. You'll create the parts, you'll create the assembly, and you'll create the drawing. I probably won't have you guys do drawings for the individual parts because that seems a bit excessive if you only have one part, or if you have two questions to do. And the other question would be I would give you guys some parts, and you would have to assemble it and do the drawing for the assembly. That is one default option that I could give you guys. The other option is I could give you guys as I kind of mentioned in that post, I could give a slightly harder assembly, which would mean there would be more points for you guys to, for lack of a better term, play around with. So it would be one question, several parts. You would have to assemble everything, create the assembly, and then create the drawing of the assembly. Depending on how complex that latter option would be with just a single problem where you guys do it from start to finish, I may or may not have you guys create the drawings for the parts as well. But that will primarily be on me, whether or not that option is chosen, and depending on how tricky I make the assembly. So I love how pretty much everybody already left. But for the 10 of you who are here, what say you?
Can you repeat our options again?
Yeah, sure. So one option is two problems. One problem is I give you parts and you create an assembly and an assembly drawing. And then the second question would be I would give you the drawings and the drawing of the assembly, and you would have to create uh, the parts, the assembly, and the drawing, just of the assembly. That would be one option. So having those two questions as one exam. The other option is a single, slightly harder question or assembly where you guys would have to do it from start to finish, minus or potentially doing the part drawings as well. But if you're doing everything and it's a slightly harder question, then perhaps not. So those are the two options that I at least have personally at this moment right now. I'm probably not going to stray from either of those. I would probably just say it's one or the other. But we'll see if I could come up with something that would be a better middle ground. But I think either of those are probably acceptable.
Yeah, I agree. The first one, it's a good option, but other people will have a different input.
Okay. So in terms of if the parts were there as well, so I'm if we go with the first option, I would likely not have you guys do the parts for, or rather do drawings for every single part. And the reason for that is because think about it like this. I am likely not going to give you a problem with just two parts to create. It would probably be about a minimum of three. Either the one where I give you the parts or the one where you're building the parts themselves, which means not only do you have, if you're looking at the assembly drawing, you're going to have probably 2 pages for the assembly drawing and then factor in anywhere between 2 to 3 extra pages for the drawing as well for the individual parts. Which that's a lot of stuff, and I know that for some people the first exam was long, and I don't want to be breaking any records. Let me just put it like that.
Yeah, that's fair.
Questions and not needing to do the full process of all the questions. Yeah, and that was a bit of my concern as well if there were two questions. I want to make sure that if that is the case, I don't want to be throwing something, like I just said, I don't want to be throwing something at you guys that's going to end up being far too insane. That is what it's looking like. And I mean, just like what just like what you said, Matt, I wish everybody didn't leave because I said it earlier. I said I want to make sure that we can talk a little bit about this, and here we have around half the class. So, I mean, if that's the consensus with you guys, then I can assume that that will be the case for the rest of the class. Um, if not, then sorry, not sorry. Oh, you guys are ridiculous. Okay. All right. It sounds like that's the case. So I'm glad that we were able to have a reasonable vote on that and kind of explain the pros and cons, and everybody else can just be along for the ride because they didn't stick around. All right, guys. Well, unless there's any other questions, I know that there's still another hour left for lecture, but I mean, we're basically done. If there's any questions about homeworks, old or new, we can talk about that as well. Feel free to just shout any of that stuff out if you have any concerns with any other things that I haven't covered so far, but I mean, that's really about it.
Hi Ethan. I'm having a really hard time getting the coordinate systems on the drawings to be, or the coordinates placement on the drawing.
Okay. And there are some little bits of nuance here and there that can make that difficult. So I agree. Which homework are you working on? Are you doing like the mailbox one?
I actually can't run it while I'm using Discord.
Okay, that's totally fine, but you can just
But
let me know
I
which one
took
it is.
notes, so
Which homework is it?
yeah, we could do the mailbox one. That's fine.
Okay. So there's a fairly simple way of doing it, and I just want to kind of at least set the stage just so that everybody is on the same boat here. I can pretty much describe it on this model, and I think you'll get a fairly good sense of what I mean once you go into SolidWorks and you play around with it yourself. And it will be on the recording. I'm still recording now, so if you want to go back and kind of look at what I'm doing one more time, you're more than welcome to. So on that model there, what I had was I had a coordinate system that was centered right at the like absolute center of, not at the absolute center of the pin itself, but at the center of the circular surface that was on the pin. And generally, if we try to create an axis, or rather a coordinate system there, like I'm clicking on this circular surface here, and it's definitely not cooperating. It really doesn't care what I think, and it doesn't want to function in any way. So the way that we can get around that is just like how we can add reference geometry to parts or components or drawings or any of that stuff. We can actually sketch in assemblies as well. Now, forewarning, I wouldn't recommend doing it often because assemblies is where you should be putting parts together, not creating new ones. But in terms of reference geometry, it's a good way, or creating sketches is a good way to create extra reference geometry. And also an important part about this is I want to choose something that really isn't going to move because, I mean, having a moving coordinate system is going to be uh, bad news for everybody. So what I'm actually going to do is I want to sketch on a specific plane. So I'm actually going to sketch on the face of this screw here. So if I click on that, now any sketches that I create are going to be on the plane that this face makes. Now it tells us, it gives a little warning, so it's not screaming at us, but it's just shaking its finger at us, telling us, hey, don't be careful, don't do anything like this, or don't create too much crazy stuff. But all we're going to do and all we actually need is just a vertex or a single point. And the nice thing about cylindrical shapes or even simpler circular shapes is that it's already saying, hey, you want to put a point here? Right at the very center of that circle. So if I click right there, now it's created a point that's at the dead center of this circular face. And if I hit escape, you can see that even when I turn it like this, I can still see the point through this geometry, and that's actually a good sign. The reason being is that now I know that it actually is recessed a little bit into the screw, since it does have a bit of a bevel to it, or kind of like a recess here. And now, just like how a regular vertex can be chosen uh, as our point for a coordinate system, I can use this point that I just designated as a coordinate system location as well. So I'm going to make sure that I'm not selecting it. I'll hit coordinate system in our reference geometry, and now that point actually does show up. And when I select it, it's saying, hey, yeah, we're in business. This is good. So it is referencing that specific point now. And sure, I don't really care about the axes. They should all be either what I want or really nothing that's too crazy or straying from the norm. And now I have a coordinate system that is based right on that point itself. And just as what I would normally do, I can go into the mass properties and use that as the location of uh, where I'm referencing the center of mass. Now, something to note, at least in this case, all, or at least the majority of this geometry is in the negative region. You can't see it on my end, but all of the center of mass values are negative, which makes complete sense. They should be. The center of mass is going to be basically somewhere in the center, kind of a little bit higher than where the guide is. In fact, I actually think that's where this coordinate system placement that it was just showing actually is. Um, yeah, it is. I probably should have made a little bit better note of that, or just that you can start sketching in assemblies as well. I wouldn't necessarily recommend doing it frequently, but it is good to keep in mind if you do have instances where you're saying, how could I create a coordinate system there? It doesn't really make sense, or rather, there's no specific vertex that I can select. However, I can create one, and I can create one by creating the geometry required to create a coordinate system, which is just going to be a point or a vertex. I'm actually curious. I wonder if you can create it on something that does move. And here I'm going to probably break SolidWorks, so we'll see. But if anybody has any more questions about stuff. Oh my god, you totally can. Now, will it stay there? Yes, it will. Okay. Interesting. Yeah,
I
that's about it.
I created a point and I couldn't select it as a coordinate system origin.
Are you still in the sketch?
It no, I'm in a different one actually. But I'll go back to it to see if I could make it work.
Yeah, take a look at it. I think we were talking about it just the other day, and I think this illustrates sort of what I was getting at without explicitly showing it, like on the geometry itself. I wonder why that would be. Yeah, just make sure that it's just so kind of like how I did it. I would just go very slow with it and just say, okay, what's the circular region that I want to select as the sketch plane? So just like how we would do it in a component creation, I would either select that face first or go into sketch, hit sketch, and then select the face, and then just put the point in the appropriate location. So it should show up right like there. And then from there, when you hit exit sketch, it should be a completely applicable point to use.
Okay.
And then beyond that, you just go to your assembly, go to reference geometry, third from the top is coordinate system. If you already have it selected, then it should auto input that as the coordinate system. Or if you don't have it selected, then you would just hit coordinate system from the reference geometry dropdown and then just select it. And then you shouldn't really have to play around with the axes. They should all be what they should normally be anyway. At least if I'm remembering correctly. I typically don't mess around too much with the direction of the coordinate system because I think that would be a bit of a bad move, for lack of a better term. I think it would just be stupid and it would be too like I'm not trying to trick you guys. At least I hope nothing that I've given you has seemed like it's been like a gotcha moment. That's not what I'm after. Those are the stupidest lessons. Anything else? Well, alright guys, so, I mean, I know there's plenty of time. I'll still be around. I'm probably just gonna have dinner now, but if you guys still have any questions about anything, just shoot me a DM and we can either hash it out in the study room or we'll try to just talk about it. So you can either DM me or email or however you like to do things best. Just let me know. All right, guys. Sweet. Have a great night. And if I don't hear from you before next Thursday, before the exam, well then, I'll see you then. Have a good night, guys.